Thank you for having me here. It's the first time that I visit the university, and just the second time that I am in Toronto, so very nice. I don't know why I left all those places. I just always think that I was following the gradient descent of temperature, just always moving into a colder place. So I don't want to move again because I'm afraid of what the next step might be. So I want to talk about something that we are working on recently, and it's like a new thread in my lab. But before that, I wanted to mention this thing between MIT and IBM. So this is a collaboration that I started just very recently, and IBM has an office in Cambridge, and it has created this collaboration with MIT. And the goal is to have researchers at IBM and researchers at MIT interested in artificial intelligence work together in tackling a number of problems. And it really is a very broad enterprise. It's not just computer science. It really touches all different aspects of MIT, from healthcare to societal benefits of AI. So it really it's really a broad enterprise. And during this process, we discovered all these people working on AI-related topics all across campus that I didn't even knew that existed. So it's really interesting. And the office is right there. This is the IBM office. So it's really like 3 minutes walk from campus to the office. And they're hiring a lot of people. So if you're interested, please, you can apply here. And it will have a nice combination of collaborations between MIT and IBM. And it's all research-oriented. OK, so that's all I wanted to say. So as you know, it's a really exciting time for computer vision. In the last 5 years, things have changed so much, and it's just starting to work pretty well, and it's having a huge impact in lots and lots of applications, from medical applications, robotics, autonomous driving, and so on. So it's a really big success for computer vision nowadays. And of course, if you know a little bit of history, you know that this hasn't been like that for a long time. In fact, some of you that are just starting your PhD, you live in a new world. It wasn't like that for many of us when we started. In fact, just a few years ago, you could put a picture like this into a computer, you run your best computer vision algorithm, and the typical output will be this. And this was very standard, and you had to publish this. And the reviewers will say, oh, yeah, I can actually see it's better than before. So, that was what it was, computer vision. It was kind of depressing, and you had to know all these different things to make something that didn't really work. Anyway, so why did it fail? Well, there were many issues. There were many things that were wrong. So maybe the data was wrong. So let's see how we collect training data for computer vision nowadays. And this is still something that we do, so probably you have done this. So you go to Google, you query for the class that you want to train your classifier on, and you will download some images. So let's say that you want to train a bedroom classifier, you go to the web, you type bedroom, and this is the images that you get back, and you collect many of those. Maybe you clean it up a little bit, and you train your classifier. But there is already something wrong with these pictures. Look at them, how nice they are. No one has a bedroom like this. I mean, look at all these things. No, there is not a single object out of place here. Just not very natural. So you could say, oh, I want to increase a little bit of diversity. You go, you query for a student bedroom. You know that you're going to get a little bit of a mess. And what do you get back? This. Look at that. This is clearly wrong, OK? There is not a single student bedroom that looks like this. They're supposed to look like this, okay? So the data was already wrong. There is a lot of biases, and the type of data that we collect, because it's not collected on the wild, it already kind of looks different from what is going to look in the natural world. And it happens with everything. Like if you query for mug, this is what you get. This is clearly not a random sample of mugs in the world. First, there is no background, but look, all the handles are on the right. There is only one that has the handle on the left. Why is this? This is the typical biases that actually, even human perception has this type of biases. But if you train a system like that, it's clearly not going to recognize marks under all kinds of visual conditions. So the data was wrong, but maybe the features were wrong also. And there has been a lot of effort into trying to develop new image features and then try to visualize them and understand what they are encoding. So here is a very famous one, the cutting edge detector. Probably well, I don't know if any of you still use it, but it's still very useful. You can still use it as a preprocessing stage for a number of things. And people thought for a long time that you preprocess your image, you extract edges, and that's your representation, and then it's a very reduced representation with respect to the pixels, so you have some hope of learning something on top of it, and then you train your classifier and whatever. But look at that. This is what the cutting edge detector is seeing. What is this? It's impossible to know what the content of this picture is. The information is already gone. This is what the actual image is. There's no way of even getting close of guessing what the content might be, so the information is already lost. There is no hope for whatever classifier you have later on training and detecting this. So, the state of the art in computer vision just a few years ago was Hawk. How many of you have used Hawk? Like, you raise half of the audience, and the rest probably deep learning. So, Hawk was, it was in everybody's toolbox. Super powerful descriptor. It didn't really work, but you start seeing a few detections that were correct, and that was already pretty amazing at the time. So one of the things is that Hawk is this complicated nonlinear function, and at the end you don't really know what the output is and what information are you preserving and what information you are keeping. So a couple of my students work in building a visualization tool that will allow you to reconstruct an input image that will reproduce the same Hawk features that you had for a real image. So it will give you like an equivalent set of images under that representation. And what I'm showing here is you train your classifier to detect people, let's say, you run it on images, and you take the highest confidence detections, and you then visualize them according to this visualization tool. And it shows this type of images. And now if you look, so this is the top detections for people, chairs, and cars. Can you make a guess of which ones are false alarms and which ones are true detections? No. Unless you have already seen this. Yeah, I mean, maybe you have some guesses. I don't know. Some people sometimes say, oh, this looks like a dog, maybe. Well, they are all false alarms. They are all mistakes. There was not a single true detection here, but when you look back at the reconstructions, they kind of look nice, no? You can even tell stories about what these people are doing, no? You see the pose, you see an action, but there is nothing there, and this is, this person there is just the cows, the rear. So there is really no, it's all gone. So the classifier, if it sees this is the input to the classifier, you can have the best machine learning algorithm you want. After that, there's no hope, it's already gone. This already looks like the object you are looking for. So this is especially frustrating, given how easy it is to see. And just to illustrate how easy it is to see for us, we created this low-resolution video that maybe some of you have already seen. So this video is a normal day on our office. We recorded this while I was a postdoc. It contains only about 20 pixels worth of vertical resolution. So some objects are only 1 pixel. But you can tell everything that is going on here. So, our visual system is so powerful. You get to see everything, you recognize, it's so easy, you make no effort, you wake up in the morning and you see. Okay, you don't have to warm up to see. And at the end of the day, you are not tired because you have been seeing all the day. It's just effortless to you. And still, training computer vision algorithms is so hard. So it was very frustrating to explain to my parents why it didn't work. They still think we don't do anything there, really. So, just to illustrate how difficult it is to solve the vision problem, if we watch the original high-resolution video, this is what it is. So, not everything was really what you expected. And the thing is that what you are interpreting into the video is really a lot more than what is actually contained in the pixels. You are putting all this knowledge about the regularities of the world into how do you interpret that video. And it's getting all that knowledge that is really hard. And of course, encoding it and so on. But you really need to have a lot of data. So data is going to be crucial here. And then, of course, deep neural networks came, and it changed everything. And now these previous demos don't hold anymore because they kind of start working. And it's just amazing the amount of progress that has been due to this. And of course, one of the things that hasn't really moved too much is that you still need to have a lot of data to train this network. So you need to have images like this with everything segmented, many objects, and you need to give all kinds of details about what they are doing, and so on. And you don't need just one, you need thousands of images like that annotated. And the way of getting those databases annotated is by doing crowdsourcing. So you hire a bunch of people on the web, thousands of people, and ask them to label thousands of images. So it's a very costly and slow process. And in fact, when you look at who is actually doing the work, this is the typical curve that shows the amount of work accomplished by each worker. So the horizontal axis is the worker index ranked by the amount of work they did. The vertical axis is how much work they did. In this case, it could be like how many images they annotated. And you can see that it really peaks. There is one person there that really does everything. So let's just hire that person, okay? Fire everybody else and hire that person. And so we have our own annotation tool, Label Me, and I knew who that person was, and that was my mother. So here is my mother labeling images. She's been labeling images since 2005, maybe, so it's just this most expert in the world on image annotation. She labels image every single day. And we just released a data, like a year ago, a data set of all the images, one part of the images that she has fully segmented. So this is full segmentations of all the objects in the picture. There are around 22,000 images that are fully segmented, more than 500,000 objects that are annotated with parts. So there are all the pixels in the image are densely annotated. In fact, this, if you know of other datasets like Coco from Microsoft, this is around the same size as Coco, but Coco was labeled by a bunch of people, put in a lot of resources, so it was an expensive process. This is just my mother, okay? So it's just a lot of work. And these are some images that she labeled, so you can see how densely annotated they are. Okay, so the thing is that that's very different from how kids learn to see. No? Kids don't learn to see because someone labeled all the single pixels in an image, not only one pixel, only one image, but all the images that you see or hear, this pixel is the rug, and that pixel is the rug, and that pixel is the rug still. You don't do those things. Kids learn in a much crazier environment. So here's an example of a kid learning. So let's watch this video.
In the summer, I like to lie in the sun and watch the birds. And I like to watch the frogs in the pond. Then I curl up in my hollow tree and dream about spring. The end.
So just like machines, kids want to have a lot of data, and they don't like it when you stop giving training data. But if you think of this particular way of learning, this is really crazy because okay, there is the supervision of the mother in this particular case, giving words to what the kid is seeing. But that supervision comes in a way in which the signal is coded also. There is no decoding mechanism for the signal. The signal are not clean words. It's also a speech signal, which is also another thing that the kid needs to learn. So you are getting supervision about something that you don't understand in a form that comes in a form that you don't understand either. Okay, so you have like two coded signals, and you have to decode them both simultaneously. So it's a really hard problem, no? In computer vision, that's not the case. Generally, you have something that you don't understand, the picture, but you have a supervisory signal that is decoded. It has a clear meaning. This is a car. This is not the case here. It's crazy. Most of the words that she is saying in this particular video don't have any correspondence to what the kid is actually seeing. So you have to make sense of all of that. So it's a very complicated way of learning. So there is a lot of work also on image captioning. In this case, you have an image and you have a caption, let's say something like this. You have a picture, and then you have a sentence describing the content of this picture. So two men sitting behind a long table. So that's also something that you need to decode, because this sentence is something that it doesn't have meaning, but still is not a hard problem. It's not as hard to decode as it is this raw speech signal, because the words are clean. Now the word to will always appear written in the same way, so you don't have noise in the observation of this particular noisy signal. You can split things into words. You still need to assign meaning to words, which is a very hard problem, but you kind of solve the low-level problem of having to also to unravel what the speech signal is and the different ways of pronouncing the same word. So the question that we had is, can we build a system that will really learn like a kid, in which there are images and there are raw speech signals, and you need to decode both simultaneously? So the input is raw pixels and then raw audio of just someone describing the content of the picture. But you don't get to see where the words start. We are not going to use any transcription procedure to translate the speech into words. That will be cheating. This is just taking the raw signal. And there is not a lot of work in trying to solve this problem. One work was done by Deb Roy, in which, for instance, one of the things that he did was to record everything that happened in his home since the day his kid was born until the kid pronounced the first word, because he wanted to find out what was that will activate the pronunciation of the first word. What are the inputs that that motivate that a particular word is the one that appears as the first one. So he has a little bit of work in this correlation between audio and so word learning from vision and speech. So he captured a lot of data. I think it's available. So this is work that we've done in collaboration with David. This is his thesis, and Jane Glass, which is part of the speech group at MIT. So this is a collaboration between the computer vision and the speech group. And the goal was to train systems to recognize images or discover objects and words from speech. So we created a big database of images and raw speech descriptions provided by workers on Amazon Mechanical Turk. So these are like different speakers from different nationalities, different accents, and all describing a bunch of images, one caption per image. So here is one example.
This is a photo of a girl standing in front of a lighthouse. The little girl is wearing a blueprint dress. She has blonde hair and blue eyes. The lighthouse in the background is white with a red roof.
So there are lots of words. Some of them refer to the picture because it's describing the picture, but there are all other things, and there is a lot of variability in how things are going to get pronounced across the database, and you'll see more examples later. So here is another.
This picture is of 2 cupcakes against a pink background and on a plate. The cupcakes have frosting and cream swirled on top of them. The cupcakes are brown.
Some descriptions are longer, some others are shorter. There is a lot of variability. So what we did is relatively simple. The idea is we'll train 2 pathways, one that is going to analyze the visual input, another that is going to analyze the audio input. The visual pathway in this case is just a standard network. In this case is BGGNet, for those that you know. And so it processes the image, and the output is going to be, at the end, some tensor that is going to divide the image into 14 by 14 pixels, and each pixel will be encoded by a 1,000 dimensional vector. What that vector is, it will depend on, hopefully it will correlate with the semantic content in the picture, and we'll have to train that system. And then there is another pathway that takes as input the speech signal. So the first thing is the audio signal is transformed into a spectrogram, which is time, the vertical axis in this case, and frequency, the horizontal axis. This is a standard representation in a speech. And because this is collaboration with a speech group, it was really hard to get away from this. No? Ideally, you want to kind of have it end-to-end and not have to compute any spectrogram, but how do you convince someone from a speech not to do that? It's very difficult. But the thing is, this is a good representation. It already has a lot of nice properties that we know will be very relevant. And then there is just a bunch of layers. And at the end, the output is going to be a signal that will take the temporal window, we'll split it into windows, and each small window will also attach a 1,000 dimensional vector. Okay, so that's what the output is going to be. So we have these 2 pathways, both end up dividing their appropriate domains into some bins and then allocated a 1,000 dimensional vector to describe that thing. And now what you want is you want to train the network so that somehow some of those vectors align with each other. So we are going to multiply all these things, compute dot products across all possible locations, all possible temporal windows, and then you compute them. You have this now 3-dimensional matrix in which you have a space here, x, y, and then time. You will have correlations, that you have some volume. We expect that there will be peaks in this correlation, so eventually once it's trained, we expect that there will be peaks corresponding to pieces in the speech domain that correspond to pieces on the input domain, in the image domain. And the way that we train this is by taking pairs of images and audio captions that correspond to the same image. And looking for maximizing the maximum value over this volume, and then taking images for which we randomly select one image and one speech audio that does not correspond, and we want that maximum to be as low as possible. So we want to find peaks whenever the image goes with the audio, and then we want to have low correlations whenever there is no matching between the image and the audio. That's all the training that there will be here. So once you do that, well, it converges, and it learns something that makes a lot of sense. So let's hear some of the examples, and what I'm going to show. So once it's trained with a lot of data, so we are using like 200,000 images, so you would say that's probably more than what a kid gets to see. But also these images and captions come from a lot of data, lots of speakers, so it's kind of a lot of variety also. Probably a lot more than what a kid really gets to see. They don't talk with 10,000 people in the first 2 years of life. So, we can argue about how human-like this training is. So what I'm going to show then is the image, and then I will play temporarily the audio signal, and I will highlight, so we'll run this system and we'll highlight what regions on the image seem to be corresponding to that particular moment in the audio speech. So here is one example.
Here we see a stretch of grass and a small road leading up to a very old ancient ruin.
So it seems to have picked up on the right things.
This is a photo of a girl standing in front of a lighthouse. The little girl is wearing a blue print dress. She has blonde hair and blue eyes. The lighthouse in the background is white with a red roof.
So it's not perfect. There are a few things that it doesn't catch. For instance, when it's talking about the hair or the eyes, it doesn't highlight anything. But still, there is a strong correspondence between the speech signal and the visual signal.
Here in this picture, there's some skiers going up a mountain.
It's very short, this one.
There's some sort of animal. It's a bird with a very large beak, and it's squirting water out of its mouth. It's right near some white flowers, and in the back is a body of water, and behind that is more trees.
You wouldn't trust your autonomous driving car, with this particular detection algorithm, but it's not too bad.
In this photo, you can see a man swimming what seems to be the ocean. You can see that there's a little building or possibly a lighthouse in the background with a stairway.
A store and two women looking at things on the shelf. One lady got on glasses.
Okay, so you get the idea, and well.
This is a photo of a few people which seem to be racing steam tractors or something of the sort.
So you get a sense also of the variability of the spoken captions. It looks very much like the traditional captions that people are using to train systems with Coco and so on, but these are just the raw speech signals. And so evaluation is a challenge because these segmentations are not going to be perfect. So we are using the dataset, the ADE20K, which is the dataset that my model label. We have also the spoken captions on this dataset, and we can correlate words because we can run also a transcription algorithm on the speech signals, so we know the words. We also know what do they match on the image, so we have a little bit of ground truth on a small set to know exactly what is the correspondence that we should find, and we have a number of evaluations, and it's much, much better than chance, and it's pretty similar to what you will get if you were using textual captions. And this is just trying to get a sense of how many words are discovered. So this is still ongoing work. This is just to show that we have some bars and some plots. But there are like around 30 different words that it seems that the system has picked up and is able to reliably find on the images. So, of course, that's one way in which kids get to learn, by just listening to speech. But kids also learn even when there is no parent around them. In fact, that's what happens most of the time. And they are constantly learning. So let's see a kid learn by itself. They like to hear the sounds, how they feel, how they touch things. And then you put it in the mouth to get that final bit of information that you need. So this is Ted Adelson's kid. Sorry?
And then the parent comes and pulls it.
Yeah. In this case, the parent is just recording happily. So So that's also another way in which you get to learn to experience the world, and that's because you have all these different modalities, all these different senses, and it's by also correlating the different inputs that you have that you also get to discover objects in the world. So that's something that we wanted to explore. And in particular, we wanted to explore this idea of this system that is self-supervised, but you still expect it to discover objects in the world. So one of the problems, I mean, this is something that in robotics people have wanted to do for a long time, but the problem is that we wanted to have robots that look like this, and what we had before was robots that look like this, so it didn't really work very well. And even recently, I mean, the robots are still terrible. There are a few that kind of walk around outside and so on, but they lack a lot of perception. So we are still at this time. I mean, robotics, the reason why we don't have like embedded perceptual systems learning about the world is because robots are still not out there. They mostly stay at homes, you know, in offices. So only autonomous cars are kind of the first robots that are getting out there in the world. But they also have a very limited type of experience with the world. No? They only are on roads. They don't get to play with things and interact with objects. So it's just a very particular way, a very particular type of robot. So one day robots will get out there and will learn very fast a lot of things. That's what I think. So there is a lot of work also on trying to do this self-supervised learning. And the idea here is that you want to develop a task that doesn't require any human labeling, but that by solving the task, you know that you have to solve some high-level cognition task. So you might need to recognize objects or understand the scene. Otherwise, you cannot solve that particular task. For instance, one example is colorization. You have a black and white picture, and you want to train a system that will add color to it. So that's a task that you can learn without any human annotations, but you know that for you to put the right colors, probably you need to know what the actual content of the picture is. And there are a number of other tasks. So here is one task that we are doing. So one of the things is you can also use all these different senses to try to learn in an unsupervised way. So this is our rendition of a one-year-old kid. This is Andrew Owens. This is the work that he did during his PhD. And the idea was we wanted to learn from vision and audio only without human annotations and try to see if the system could develop some higher level concepts. And what he started doing was he went with a drumstick, hitting everything he encountered in the world, and record both the sounds that it makes and the visual aspect of what he's hitting. And the idea is that if you train a system to relate both this visual and audio input, the system will have to know about materials because things make different sounds depending on the material they are made of. So here is the data he collected. He's been hitting things for a long time. So basically for a few months he was just going around and hitting everything. He entered every office and started hitting everything he could see. Not people, people were not hit. So he called this dataset the greatest hits dataset, and he collected around almost 1,000 videos, and with multiple hits and scratches. He also scratches the surface with the drumstick, and there are more than 46,000 hits and scratches. So it's a lot of data combining both audio and vision. And it hits all kinds of materials. There are a lot of materials here. Okay, so then the system that we tried to do was the following thing. We want to have a self-supervised system, and one way of doing that is you take as input the frames, just the RGB values, without the sound, and you train a system to predict the sounds that you should hear. So the ideal result here will be that you put a silent movie in, and it outputs the sounds that you should hear with that movie. And in order for you to be successful at that task, you need to understand what is going on here. Otherwise, how could you put the appropriate sounds? Well, the other possibility is that the network just totally fails, and then that's it. So here is how the system works. So first, we need to encode the sound signal, and this work was done a few years ago. So at that time, it was really hard to reproduce any type of sound with a neural net. So again, we were using spectrograms as a way of encoding sounds. So This is the spectrogram. In this case, it's cochleogram because the filters are selected in a particular way to match more or less what the cochlea in the auditory visual system, auditory system in the human brain is doing. But just a spectrogram could have worked, a normal spectrogram. So here there are 40 bandpass filters, and what you see here is the horizontal axis is time, the vertical axis is the frequency, the central frequency of each channel, and then the amount of energy that outputs that particular filter over a small window of time. So dark here means a lot of energy. So that's how we encoded the signal. So our goal then is, given the video, we want to be able to generate the cochleogram. And one nice thing about this is that once you have this, you can actually reconstruct the raw audio signal. So the first thing was to realize that indeed, when you hit different types of materials, you get a different signature in this spectrogram. So this is the average spectrogram, cochleogram, when you hit cloth, and it is aligned with the moment of the hit. So just by looking at the moment of maximum intensity in the sound, just aligning with respect to that. So you can see that the average, it shows a lot of low temporal frequencies. If you hit the ground, rocks, then you get much higher much higher temporal frequencies. And so this dark line here is just the moment in which there is the hit. This is grass. It really just doesn't make too much noise. So you can see that there are different signatures, so it makes sense that this task is going to be possible. So the way that we train this is just another standard tool in the neural networks toolbooks. So we take the video frames and we filter each frame with, in this case it was an AlexNet, it's a very simple network. One particularity is that each frame, instead of being a color image, the RGB channels were used to encode 3 different frames. So R was T-1, then T and T+1. So you get 3. You get to get a little bit. You get to see a little bit of motion already within this this network here. And then the output was fed to a recursive neural net, and the output was the cochleogram. Well, an embedding that will allow you to index the cochleogram. So that's how it works. One thing is that once you have this, you need to reconstruct the audio. And because this estimation here is very low frequency, you are missing some of the details when you try to do these things. If you just reconstruct the audio sound from this signal, it's not very nice. So we just play, in this case, a simple trick that is very standard in texture synthesis. You have your database of sounds, and the only thing that we did is you take one patch in this temporal spectrogram, this long spectrogram. We take one patch, and we query for the database for which is the one that has the closest spectrogram, and then we borrow the audio signal and we put it there. Okay, so the way that we generate this waveform is just by copy-pasting pieces of sounds from the original database. But they are indexed by the output of the network. Okay, so let's see what happens. So we train this with thousands of videos, and then what you're going to hear now is the output of the system. So what you will hear is not the real sound, but the sound synthesized by the network. So let's look at that. So it's not perfect, no? It differentiates between scratches and hits. It's able to detect the moment in which there is a collision. We didn't train the network to know what a collision is. So it had to discover that the moment of impact is when you are going to generate the sound. So it had to learn all that from it by itself. The materials are not perfect all the time, so you can hear some of the noises are not super accurate, but it differentiates between hits and scratches. Just to get a sense of how good it is at matching materials, what you will see now is the input video that I showed just before, and here is the pieces from the database from which is actually borrowing the audio. So it's not perfect, but it's still much better than chance, and this is already a few years old work. Here is another example of a video. Okay, it's not very good here. This system was trained in Boston, and just as here, there is no liquid water. It's all frozen. So it wasn't really expected to see this type of data. So one cool thing, though, is that even though we trained the system to only react to the drumstick when you were hitting surfaces, you can actually check how well it generalizes to other videos, and let's see what type of sounds it generates. So here is something we didn't train with, and you'll hear what it sounds like. So let's watch the video. So it's pretty cool that still it reacts to the point of impact, and it puts the sound in the right place, in the right moment. Of course, the materials and everything is kind of wrong, but it was kind of surprising, no? So it's detecting these accelerations and change of trajectory and just putting hit impact sounds there. This is another one. This is quite amazing how well it generalizes to these things, no? It makes you think, okay, these networks are not just overfitting crazily to the data, no? It kind of does something interesting, yes?
So this means you can throw a bunch of balls at the scene and then listen to what you get and do a 3D reconstruction?
Yeah, that's a good point. So we are working on things related to that, but this particular network wasn't really trained to do anything like that, but I think that you could do 3D reconstruction, yes. Okay, so here is another example. This one is just a total failure. When the drumstick was up, it also detected a collision because of probably the way it was stopping. So it's not magical. And then we did a study to evaluate the system. We did a study on real or fake. So we showed images to people and with the audio, and we asked them to tell us if it was the real sound or it was a fake sound. So if the system works perfectly, people should be a chance at this task. So you should have like 50% performance on this task, no? Totally random. So here is an example of the task. So now your task is to say which one was fake, which one was real. Okay, let's reveal the answer. Yeah. So this was the real one. And this is the actual performances. So this is our model. It fooled people 40% of the time, so still people were better than random, so it's not perfect. If you do just image matching, you still get pretty nicely, and this is random, if you just take a random sound. So just to show that this problem, it isn't that hard in this particular data set, because the moment of impact is well aligned. So it's only about the materials, and people are not that good. So even random was still already pretty good here. But another interesting thing is that, so this requires you intervening in the world. So you have to interact with the world to make it sound or feel it or whatever. But even when you don't interact with the world, when you are just a passive observer in it, you still get multiple senses. You still hear things and you still see things, and you can still learn a lot from it. In fact, you probably can learn from it more than you can learn from by touching them. But anyway, so here is the idea is to do the exact same thing, but instead of having interactive sounds, just by listening to ambient sounds. So when you are in a scene, you are going to hear lots of things, and what you hear is a mixture of all the different sounds that appear on that scene. So imagine that you want to do the same thing. You want to predict what those sounds are. It will force you to understand the scene. So there are lots of objects in the world, and they all make different sounds. So you hear all these things, and you have all this mixture that are telling you things about the auditory world, things about the visual world that should correlate. So just like in the speech case, you should be able to discover objects by just correlating these two signals. So here is an example of the type of videos that we use to train. So the nice thing is that now you can take a system and make it watch all the movies that you want. And there are thousands of movies out there. Many of them are really cheap, like these ones. And when you watch them, you know why they are so cheap. And now the task is the same. You take your input frames and you try to predict what you should hear. And you can train the system. So let me open a parenthesis here. And let's see what some hint of what we can expect to find inside a network that is trained to solve that task. So this was some time ago, this 2014, this long time ago now, and we were working on scene recognition. The goal is you take a picture of a place and you want to know what type of place it is. So if I take a picture here, I want the system to tell me this is an auditorium. And this is a problem that we've been working for a long time in the lab, scene recognition. And there is this particular demo that you can play with and take pictures and it will tell you what they are. So we collected a lot of data, we trained a neural net, and it was working really well. And it was very surprising because that was at the time when all these things were starting and people were all continuously amazed by all the things that were happening. So here's an example. Now you take this picture and it will output, it will tell you, okay, this is a swimming pool. Or a picture like this one and it says auditorium. It just works fairly well. So why does it work so well? So here is another example that got me really puzzled. So this is a picture of an hotel room and it says hotel room and then bedroom, but hotel room with slightly higher confidence. I mean, it's just already amazing. No? This picture is not especially well framed. How can it tell that this is an hotel room and not a bedroom, just a normal bedroom? And then I took this other picture and it still say hotel room, even now with a larger gap with bedroom. And this just really doesn't contain much information. So how can it do it? Well, my guess at the time was, well, it has to be detecting this lamp here. This lamp is just very hotel-like lamp. No? This is not a lamp that no one has at home. Okay? At home you have other things. You don't generally have a lamp that looks like this. Okay, maybe you do, it's perfect. But this is, it kind of tells you hotel room. So I thought, okay, this system has to be, somehow it has learned to detect some objects and is reacting to those objects and is really localizing them. It doesn't matter where they are on the visual field. So when you train a network to do this place recognition, what happens is that when you look at the units inside, indeed they are doing object detection, and not just a few of them. Around half of, in AlexNet, half of the units in the last convolutional layer, you can attach a semantic meaning to them. And if they were detectors, they will score pretty well with respect to the state of the art like 5 years ago, well, with Hawk. Okay, so it will be a very good Hawk detector. It's not perfect because it has not been trained to detect those objects. It just discovered that those objects are useful and it's learned to detect them. So there are units that react to faces, billiard tables, the hotel room lamp, screens, and it's detecting them on images. And this is not, I mean, these are the top activated images, but you can keep looking and they are screens and screens. So it's just a very good detector. This one is detecting like baseball fields. So it works really well. And it's not being trained to do this task. It's just being trained for the task of attaching a single label to the full image. So it's not even a localization task that it has been solving. But still it's able to find these objects. And then there are other half of the units that we don't really know what they are doing. But they are doing like shapes and textures or maybe some other ways of encoding the scenes. But there are half of them that you can put meaning to them. So it seems to be that when you solve certain tasks, the network might be solving another task that is relevant for the task that you want, and maybe the task that the network is actually solving inside is even more interesting than the one that you are trying to solve. So in this case, it's doing object segmentation, which is even better than place recognition. So we actually had a system. So this is a property that we observe in many networks, that when you look inside, you can actually attach meaning to the units. They seem to be interpretable, which always been assumed that neural nets are like black boxes. And that's really the case when you train a network to solve the ImageNet task. In ImageNet, there is, because the output at the end are just objects, there is not really a clear representation that you should build inside. It's going to be mostly shapes and pieces and so on. So when you look inside, it just looks like a distributed code that doesn't have any meaning. But if you have tasks that require a representation that has more structure, that structure will become interpretable, and sometimes in the network you can see it. There are things that you do in the regularization that might destroy that, but if you take care of a few things, you see that structure emerging inside the network. So we had a paper studying what types of regularization destroy that and which ones make that appear. And in particular, we have a system that you train a network, you feed it to the system, and the system will automatically attach labels to all of the units. And it's very cool because then you can see what happens. For instance, as you are training the network, you add more and more iterations, you can see how the concepts evolve within the network, and it's just very useful for debugging, you'll see that it's doing the right thing. If the interpretation makes sense with respect to how do you think the network should be solving the task, it's like a good debugging tool. Okay, so I close the parenthesis here. So the message here is that when you train a network to solve particular tasks, inside the network it could be detecting objects. So let's see what happens with the network that is trained to predict sounds that are ambient sounds. In this case, it's not just hits or scratches with the drumstick, which is only about materials, so the representation will not look like anything. Here is more semantic. You want to predict that you are going to hear voices or the noise of a car. It has to detect cars. Otherwise, how it will be able to predict that you should hear a car when you see one car? So we train this system with a Flickr video dataset. We use 180,000 videos, 10 random frames, and the goal was to predict what is the spectrogram of the sound that you should hear. So we didn't actually reconstruct the full sound, so I don't have a sound to play. I think it will be very cool, but I don't have that. But we trained that system to predict the sound, and it's working pretty well in trying to predict the spectrogram. But the interesting piece to me is what did the network learn inside? So when you look inside, you find indeed that there are units that respond to people and they actually localize the faces. There are several units that detect people in different sizes. It will detect babies, which there are lots of Flickr images with babies and they make a very special noise. Crowds, then the water, and it localizes the water, the ocean. There is a unit that detects cars. It's not a really good car detector, but it clearly is detecting cars. So here is the more images of the unit that detects faces. So you can see that there are basically no failures here. And it's just trained with sounds. It never really was trained with human annotated data about faces. This is the one that detects cars. This is not as good as the face one. There are mostly cars. There are a few things that are not cars, like this here, or I don't know what is this. So it's not a perfect car detector by any means, but it clearly shows a tendency to detect cars. And these are a bunch of classes that we found that emerged within the network. It also discovers instruments when we train it with a database with sounds from instruments. There is a unit that detects guitars, another one that detects keyboards. And you can actually localize the source of the sounds in images. So here is the sound that gets associated with water. And that's the region in the picture that motivates that sound. And here is people. So what you're hearing is just the center of the cluster for that particular audio class. This is another example. So it's pretty good at detecting these things. And there is also, more recently, another pieces of work, in particular from Andrew Zisserman's work, that also are trying to learn jointly from vision and audio and finding these correlations. There is even older work by Virginia Sa that was trying to show that if you learn with two modalities, you can discover properties of the world, because the thing that generates the sound and the pixels that you get to see, what is that hidden cause that is common to the both things is the semantic label, the semantic object that you are looking for. And because they produce things in such a different way, there is some hope for you to find them automatically. And there is also some other work, and they try to do like sound predictions by like lip reading or predicting what are the locations in an image that are producing a particular sound and so on. So this is a very interesting line of work. So this self-supervised learning, and there are many other tasks that you can imagine on self-supervised learning that will produce the emergence of higher level concepts. And we have actually explored all of these different tasks and run this network dissection, trying to find what are the meaning attached to each unit once you train them. Sounds seem to be the one that is producing more higher level concepts, although there is another one that is when you are tracking things on time, also produces concepts. They are not getting even close to how many concepts emerge when you do place recognition. That one really gave a lot of different concepts. This has not been as rich. But still, there are a lot of things that generate objects. Some of them actually don't generate any objects. Some of the tasks can be solved by just learning very good low-level vision. And then there is no hope for objects to emerge. So you might have maybe faces, because faces are so ubiquitous that sometimes are very useful for many different things. So I think that is a very interesting area of research, working on this self-supervised learning domain and try to develop tasks that the actual output is not solving the task. You actually don't care. The task is just some excuse to build a representation that is really what you care about. That is the most interesting thing. So that's one of the things that is motivating our work in the last few years. So I'll end with this. I think we are on time. Yeah. If you have questions, I can keep going, by the way. Yeah? But,
we'll do questions. Thank
okay.
you so much.